object-oriented discussions in C++. So I hope my slides are visible, right? Can you see my slides?
Yes,
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 sir.
sir.
Yes,
So we have talked about classes, the basic layout of an encapsulated entity and instances as objects. We have discussed that there is a great principle of information hiding by specifying private or public access. We typically provide specify public access to the interface which others need to use, and provide private specifier for the details of the implementation. It is typical that data members are with private access and methods are with public access, but it could be some data members could be public and some methods could be private as well. And then the most important thing that we have seen is every class has a constructor and a destructor. The constructor is an initializing function which gets automatically called often when you are instantiating an object. And that constructor is a special function which has no return type. It returns nothing, but it has an initializer list where the data members of the object can be initialized. And as soon as the initialization is over and the constructor body is about to be executed, where you might put more, codes to get started with. But as soon as the body of the constructor starts, at that point, the object is said to be in life. The lifetime starts. And on completion of the body, the control comes back to the instantiation point and you keep on using it till the object, goes out of scope, or you explicitly say that you don't need it anymore. And at that point, the destructor is invoked with the implicit this pointer. And in the body of the destructor, if there is some deinitialization required, you can do that. And when the destructor completes, the lifetime of the object is over and that object is no more available to you. So we have seen that in terms of the lifetime, there are two important things. One is the memory must be available where the object will reside, and the initialization has to happen before you can use it. Similarly, the deinitialization has to happen before you can release the memory, and finally the memory has to get released. And we have seen that there are typically three kinds of lifetime that can happen based on the part of the memory or the behavior where the object is created. If it is in the function scope or in some block scope, or it's a function parameter, then these are all automatic, where as soon as the control passes that point, the object's memory is already available in the stack frame of the function, and the constructor is invoked. And when that scope ends, the destructor is automatically invoked. So that is why these are called automatic objects. Then we can have static objects which are not in any function scope, which are constructed even before main starts and are destructed after main returns. So they stay there for the entire lifetime. And static objects are given memory in the static memory segment of the program. And finally, there are objects which are dynamically managed by us, the developer, for which you need to do a new on the object type. With new, first a dynamic allocation is done using operator new or malloc, something like that. And you acquire a memory from the system and pass on the address of that memory to the constructor for the normal construction process to happen. Similarly, a matching delete will need to be invoked when you are done with the object. So while automatic objects lifetime is always limited within a lexical scope, and the lifetime of a static object is limited around the lifetime of main, the whole program execution, the lifetime of a dynamic object can be managed by the user. You can create allocate and create that object in one function scope, and actually delete, deallocate in a different function scope. So the override is yours. So now going forward, we will see some more core operators in this, some bit more on the object lifetime examples. So we have talked about the construction and initialization process. So in that, there is a question as to if there are more than one data members. So which actually this relates to the lifetime concept again. Suppose I have a class X which has two data members, M1 and M2. And say I have some global functions to initialize them. These functions have no specific purpose. They are just, I mean, for our understanding to see the order in which things are happening. So in the constructor of X, look carefully. In the initializer list, I'm first taking M1 and initializing it with the value of init M1 when M1 is passed to it. So parameter M1 is passed to this function. This function is called, it returns a value. And with that, data member M1 underscore is initialized. Similarly for M2. You run this program, you'll find that first you get init M1 underscore message, then init M2 underscore message. So you know the order in which they are happening. Now the question is, what is the order in which initialization will happen? Will it happen based on the order in which you write them on the initialization list? The answer is no. Suppose you order, you
So we can't
So we
hear you.
can't hear you.
can you hear me now?
Yes, sir.
Yes,
Yes.
sir.
I got disconnected. There is always some problem with the network. So I'll go back. So we were discussing about the initialization order. So you can see that between the two constructors on the left and right, the initialization list has not been changed. But between them, the order of the data members have been changed. So now you see that when you run the program on write, you get init M to it. In the initializer list, you can write the initialization expressions in whatever order you want, but the execution of the initialization, the order of initialization will happen according to the order from the beginning to the end as they are defined within the class. This is a very, very important observation and may have serious quality consequences to note. So let us take another example. Let's say we consider a simple string class. So on left, it is on the C style. So you have, you are defined a string S on which nothing happens because it's C. It just, the memory has been allocated on the stack, and you initialize the str pointer by making a duplicate of this constant string partho, and then you put the length of that by computing the length of the str data member, right? So this is the initialization, then you can print it. On the right, we are doing it the proper C++ class style. So we have two private data members. We initialize them based on whatever has been passed. So what I do here is now I say that I have a string object S, which is to be initialized with a constant string partho. So char star S actually points to partho. I do a str dope on that to initialize str underscore and then take the length of it, and the program. I change the order of the container and the length in the string class definition. Suppose I just swap these two. Let's say I've swapped these two. As I've swapped these two, this is the behavior that I get. The program crashes. I get an unhandled exception. Why do I get that? Since I've swapped these, when the constructor is invoked with s pointing to partho, len is the first data member. So even though in the initialization order it comes second, this is first what is to be executed. So this is to be initialized. So len is initialized with strlen on the str underscore data member, which has not been initialized. So it has a garbage. It has a garbage pointer. So strlen on this garbage pointer actually crashes. It gives an unhandled exception because there is no proper memory allocation here. So the code actually fails in this initialization just because of the fact that you have swapped the order of the data members here. So it has to be you have to be very careful. And that's another quality coding rule we are learning is when you write your initializer list, you need to make sure that if the initialization of one data member is dependent on the other, then the data member on which the other is dependent has to occur earlier in the list, like cat star str has to occur earlier than len, so that your initialization will actually work. Otherwise, just making the right order in the initializer list does not actually help. So this is now there are a number of examples that I have given here, so which I would not go through line by line in the class, but you should study them, should make it a practice to study this code and understand what is going on and execute them. There's instance of the rect example we had taken earlier. So now this is your point class. So point class has two data members, x, y, and a point constructor, point destructor, and a print. And the rect class is based on the point class. So it takes two point class objects, top left and bottom right. So when you write the constructor for the rect class, you need 4 integers. The xy coordinates of the top left point and the xy coordinates of the bottom right point. So these are the 4. And with that, what do you need to do? You need to first construct this data member. Earlier, you were just using data members which are of predefined type, but now you have a data member which is of your defined type, user defined type, UDT. So you need to actually construct that. So this is the data member, and these are the parameters you are passing to it. So this is actually will invoke the pointer, the constructor of the point class, and construct the point. Similarly, this will invoke the constructor of the point class and construct point br. So you can see that when I'm constructing any object where there are data members which are of other user defined types or classes, they are constructors in the order in which these data members are defined will be invoked and constructed before the construction of the class can complete. Similarly, when it gets to destruct in the rect, nothing is specified, but the order of both of these TL underscore and BR underscore will have to be destructed by the destructor of the point class, and then their call order would be opposite of their construction order. So here TL was constructed first, BR was constructed next. So when the destructor is called, BR will be destructed first and TL will be destructed next. And that is the general principle which will generalize. You can see the runtime traces, you can run it yourself and see that. And that is a basic lifetime principle that you'll always have to keep in mind to write good proper code. Here is another example to define name and address classes. And using that, we are defining here a credit card class and doing some transactions with that. And the traces are discussed here. So I will not go through. You just study when you do this, do prepare on this and understand what is going on. If you have any doubts, write on the Moodle forum or ask me over the mail. Now we will move on to two very important other functions, member functions that are also available or also needed for managing the classes. So let us see, when you are defining an object of, say, complex class we have seen, you can do C1 initialized with a list of initialization values, or we have seen we could write it some creates a new object from the parameters using the constructor complex colon colon complex, which has two doubles. But I can also construct an object, say C1 has been constructed. I can also construct an object C2 from C1. And this is the way I write it. Or I can write it in this initialization notation. So this is like the function notation. I can write it in the initialization notation also, complex C2 initialized with C1, which means that I'm trying to construct an object C2 from an object of the same type. C1 is an object of type complex, and I'm trying to construct another object C2 which is of the same type. So this is known as copy constructor, that you are trying to create an object by copying. So naturally, what will that copy constructor look like? It is a constructor, so it has to have the name complex. So this part is easy. And what does it take here? It takes another complex object. So it should take complex ampersand. That is, it should take this by reference. We'll see more as to why should it take it by reference, but we have said that whenever we pass an object in C++, it is better to pass it as a reference. We pass that object as a reference. And then we put a prefix const to say that the object you are copying from. So this says that the actual parameter C1, whose reference will be available within this copy constructor, cannot be used to change C1. So that should remain a constant. So that's a typical copy constructor. Let's look at examples. So now we have the complex class again. Here is the constructor, and here is what I have defined as a copy constructor, complex const complex ampersand C. And so how do I want to do it? I want to copy member by member. That's the most obvious way to copy. So the real component of C is C.re, and the imaginary component is C.im. So I take C.re and initialize re. So this is basically C.re is used to initialize re, C.im is used to initialize im. And then within the body, actually there is nothing to do, but I have put a message so that we can understand what is getting called, right? Destructor does not change, everything else remains same. So now I do put these object construction. So naturally the first one is a construction by this constructor, first constructor, double double. Second one is a function notation for the copy constructor. So it should construct based on the object C1, it should call the copy constructor. The third one is also a different notation for the copy constructor. So these two should use copy constructor, and then you print all these three objects. So all of them should be copy of each other. So if I invoke, I see complex CTOR, which is this function is getting called. Then in the next two instances, I see the complex copy constructor are getting called, the same objects. Then we print them. And then there are three instances of the destructor called, first for C3, then for C2, then for C1. We have given the identical values, so you cannot distinguish them, but that is the order in which they will happen. So that's the purpose of a copy constructor. Now you will obviously ask us to why do we need copy constructor? Why do we need to have copy? At this point, recall the function call mechanisms in C++. So we have noted that we can call by reference or we can return by reference. If we call by reference, actually an alias is passed or an hidden address of the actual parameter is passed. If we return by reference, then an alias or hidden address of the returning object is passed. So it is fine. So there's nothing that involves any creation or destruction of objects. But if I do a call by value, what do I need? Call by value is actual parameter is copied to the formal parameter. Now, when it was int parameter or when it was double parameter, that copy was easy. But when it is an object, like a complex, I need to have a copy mechanism to copy the actual parameter into the formal parameter so that the formal parameter can be used in that function. Similarly, when we are returning by a value, I need to make a copy or clone of the computed value and need to make that copy available as a return value. So copy constructor is required for making function calls. Without that, call by value mechanism cannot be supported in terms of an user defined class, an object. So let us see what happens here. So we have the copy constructor, the same double class, and we have a function display which takes a parameter of complex by value, cparam, and then displays it, which is just for illustration. So what will happen? This is where the construction happens. So the constructor is called ctor. This has been done. Now you are calling display with C. So what has to happen? This is a call by value. So C has to get copied to cparam. So which means cparam will get constructed by copy construction from C. So this copy constructor will get invoked. So copy constructor gets invoked. Cparam as a copy of C, and then with that the display is called, and therefore displays the same values as I have given in C. Then display reaches. So this object has been created here. The lifetime starts here. Now the scope ends here at the closing parenthesis. So at this point, what has to happen? This object goes out of scope because the object is naturally on the stack frame of display, which will be now deallocated. The object is not accessible by name. So at this point, this object will have to get
Sir, we cannot hear you.
I had again got dropped. I hope I'm audible now.
Yes, sir.
Okay, so I'm back with the presentation. This is very irritating, the network. Anyway, so you can see that I have used the copy constructor to be able to do a call by value. Similarly, I can use it for return by value as well, right? So this is very this is important from that perspective. So what should be the signature of call by value? Now, this is the signature that will be the most common. Is you take the value that you want to copy from as a reference and make it a constant, so that within the copy constructor by mistake also this does not get changed, right? So this is a common signature for a copy constructor where source cannot be changed. But occasionally we will drop this const. At a later point of time, I'll show instances where you need to change the object you are copying from, which is somewhat of a immediately non-intuitive, but it's kind of, you can think of that you are trying to do not exactly a copy semantics, but kind of a move semantics, that you are taking away the object from what it was to the new object that you are creating. We'll talk about that later. So occasionally you use it without the const, and you can use it with volatile also, which is very rare. So don't think about that. Now, naturally, it is possible. I mean, you can write think of writing a constructor which takes a pointer to the class, or a pointer to a constant object of the class. You could take these, but these are not copy constructors. These are just other constructors, overloaded constructors, which you can have, which you can use, but they will not be treated as copy constructor in the context of the copy semantics. Now, the final question is, in the copy constructor, what happens if I, instead of writing a reference parameter, if I write it as a value parameter? What if the copy constructor takes the parameter as call by value? Naturally, you'll see that why are we providing copy constructor? So that we can support call by value. So at the time of call, a copy will be done. So what will happen here? If I'm doing a call by value, for example, in this case, I'm doing a call by value. So I want to copy C to C param. Now that will invoke the copy constructor. If this copy constructor itself is a call by value, then I'll again need to make a copy. So it will call the copy constructor. Now that copy constructor is called by value. So it needs to make a copy. It calls the copy constructor and so on. So if I make it a call by value, then it will, when it needs to be used, it will get into an infinite recursion, because every time I pass the parameter, it needs to call itself, right? So this is the this is the trap that you get into. You can try this out and see. So it is not possible to pass the parameter by value. You need to has to pass the parameter by reference, and it's preferable that you pass it as a constant reference, right? So this is the whole point about. And here are more examples. Again, I will not go through the details. So you can go through. For the point class, for the rect class, we have provided the different parameters, different copy constructors as well to show you. And we have provided copy constructors which have mixed signature. For example, here is a copy constructor which takes 2 points. So here is a kind of a pure copy constructor. So these are kind of overloaded stuff. This is the pure copy constructor which takes a rectangle and provides a rectangle. Right? So this is what you'll be able to execute and see. So this is the trace of the object lifetime. You should actually run it yourself and see. Otherwise, you have to carefully read through this example. Now, suppose, like the constructor, you said that it is possible to write a class where I do not actually provide a constructor. Then the compiler provides a free constructor which does nothing. So similarly, if I have a class which I use in the context of call by value or return by value, but do not provide a copy constructor for that class, then the compiler will not give a compilation error. It will provide a free copy constructor. Now, what does the free copy constructor do? Free copy constructor does not know how to. I mean, it's a compiler generated function, so it does not know what to copy, how to copy. So it does something better than the constructor. What it does, it takes the bit layout of the memory of the object it is copying from and lays it out in the object it is copying to. So it just copies bit by bit. Okay. So if you look at that, in some cases you may be okay with that. For example, let's say complex. It has double and real, real and imaginary, double data members. This is a constructor. This is a copy constructor. I have commented it out. And I'm again executing the same code display. So when you have the copy constructor is called, the message is printed, and you have a destruction here. When you do not have that, we have not provided, the compiler has provided a free copy constructor. So at the point of call, a copy is happening by the free copy constructor, and you can see that display is working correctly. Wow, because C has a memory layout of 2 double values. It is just taking that and putting that whole memory layout on the C param. So C param eventually turns out to be a correct object, though it has not been constructed. So kind of you have taken a backdoor. So display works properly. Interesting thing to see is that the destructor gets called twice because you have not provided a copy constructor, but compiler has provided a free copy constructor. So a construction has happened. So when display goes out of scope, that C param object will get destructed by the destructor of the class. So it gets destructed, then finally C gets destructed. So this is the behavior of the free copy constructor. So you'll kind of feel that, well, if that is the case, then the life is fine. I mean, why do I need to write free copy constructor? Right? That's what you may be feeling. That at cases may be okay, but please remember that when you construct an object, then it is just not setting a value to the data member. It may be in turn constructing other objects which are data members therein. It may be allocating memory as a part of construction. It may be initializing that memory that you have allocated and so on. So construction is not same as bit copy. Let's see for an example. So I have a string class. Right? We have seen this construction before. I have provided a global function here, which takes a string object by value and converts it to an uppercase set of characters, and then prints that by using the data member print. This is what it does. So I construct the string object by the constructor. I print. I see partho in lowercase, and it gives a length which is 6, which is correct. Then I call str to upper S. So what it does, it calls the copy constructor. So in copy constructor, what we'll have to do, I'll have to construct a object which is a copy of this string object S. So that string object S, the string object S has an allocated string pointer, character pointer, and a len value. So I use that string which s.str, the character pointer is pointing to in the S object I'm copying from. I make a duplicate of that, and that string I copy from str. So s.str and the str, that is here a.str, necessarily point to 2 different allocated memories which incidentally have the same set of character sequence. Similarly, I copy the len. So I have a completely new object constructed in the same way as a string object. So when I'm done with the copy, A is a copy in terms of having a new str pointer, but pointing to the same array of characters and has the same len value. So in A, I make changes and then I print A. So I get the uppercase printed because I have changed to uppercase. And I come back, I return from here. So it is destroyed. Destructor needs to free up the allocation that I have done through str duplicate do. So it frees str, but there is no message given, so you do not see anything. So A gets freed up. I come here, I still have S, which is, so mind you, S, so A has been destructed. So A dot str is deallocated. So it does not exist anymore. But when I come back, I'm using S dot str in the print because this is the form parameter which has not been changed. So I print again and I get the original non-uppercase value here. Everything works fine. So what is we have done in this, just to know the terminology, we have done a deep copy. Now, what would have happened if I would not provide the copy constructor here? It will copy it bitwise. So the value of a dot str pointer and the value of s dot str pointer would be same because I'm just bit copying. So I have made a copy of the pointer, but that pointer, both pointers will point to the same because I have not done any allocation, I have not done any copying of values. So that is called a shallow copy. When a pointer points to an object and you copy that pointer without copying the object it is pointing to, it is a shallow copy. But what we have done here is a deep copy. We have copied the pointer here, taking that pointer here, and we have copied the object that it is pointing to. So it has done a deep copy and things are very fine.
Excuse me, sir.
Excuse me, sir.
Let's comment out.
The screen
Yes.
is frozen to the previous slide.
Which one?
The complex free copy constructor.
Here.
Yeah,
Let me share it again.
Page number 20. Yeah, it's frozen to that page.
Now, do you see the string example?
Yes, sir.
Now you see the string example. So I was talking about the string example. So this is the constructor. This is a copy constructor. This is str to upper, which is taking and putting it to uppercase and then printing it. So this is where actually a deep copy is happening, because I'm not just copying. I'm not just doing str copying the value of s dot str. That would have been a shallow copy. That just the pointer is copied, but it will continue to point to the same object. But what I have done, I have taken the original pointer, created a duplicate string, which means I have allocated equal amount of space, copied every element using this str_do function in the C standard library. I'm sorry. And then that pointer is what I have returned, that new allocated pointer. So the pointer is copied and so is the object. So that is the whole notion of deep copy. Now I'm going to the next slide. Is the change visible now? Is the change visible?
So we can see
Hello?
21 right now.
You don't see you don't see 22, slide number 22?
Yes, sir, it's visible now.
Yes, sir.
Okay. It is taking a little bit of time. Okay, I'll go slow. Okay. So now in the same example, what I've done is I have commented the copy constructor. Can you hear me right?
No, sir. There's echo.
Sir,
Sir,
there
it's
is an
echoing.
echo effect.
Oh, I don't know what is wrong today. Let me go out and come in again. Can you hear me now?
Yes, sir, it is clear now.
Okay. Something goes wrong. So you can see slide 22.
Yes, sir, it's 22.
So now in this, what I have done, I have commented the copy constructor that I had written. The compiler will not give a compilation error because this is it will provide a free copy constructor. Now, but with that, with this commenting, this is the behavior that you get, that your code crashes. Why does it crash? Now, if you do not comment with the user-defined copy constructor, this is what we had. But what will happen if I comment it? What does a free copy constructor do? It will only do a bit copy. So when this call by value happens to str to upper, s to a, s.str and a.str, both of them, they are different locations where they are stored in different objects, but both of them have the same address value. So they are pointing to the same array right now because it has done just a bit copy. So the str to upper function works pretty fine. So I got s.print here on the right. I got str to upper s, that print going fine, the uppercase print. Now the str function to upper function returns and this scope closes. When the scope closes, a, the copied object will get destructed. So that's destructor is called. So a.str, that pointer is freed. Now it happens to be the same pointer as s.str. So freeing a.str creates the side effect that s.str, which was in the main function and should not have been changed, actually is also freed. Because you had done a shallow copy, you had done just a bit copy. Therefore, when you want to do s.print here, and you are trying to print str, it is pointing to a garbage which is already corrupted, which has already been freed, and that is why the code crashes. So that is a difference. You can see that. So it is always advisable that you provide a copy constructor properly for your class. Right? You can see more. Construct more examples. So the last, I've moved to slide 23. The last of the important operators or member functions that a class needs is known as assignment. So for the complex class, I'm writing an assignment operator, copy assignment operator. So let's see where it is required. So here are the object definitions. So these C1, C2 are constructed by the first constructor. C3 is constructed by the copy constructor. You print the values, you will see them here. But then what I'm doing, I'm assigning C1 to C2. See, this has a sense of copy, but this is not a copy constructor. This is a copy assignment. What is the difference? What is the difference between this and C3 within bracket C2 in this complex and this? In the first case, C3 did not exist when I started doing this operation. I'm creating C3 by this operation of copying from C2. So it is a copy construction. But when I write C2 assigned C1, then I'm doing the C2 already exists. So I'm assigning the value of C1 onto C2. So I'm going to change the values of the data members of C2 from the values of data members of C1. Right? So that is the important difference. Therefore, in terms of the parameter, you will see that both of them takes the parameter by reference, and that reference is constant typically, because you don't expect that you are copying C1 to C2 and C1 gets changed. You will expect C2 to change. The name of the operator, the operation is assignment, and the name of the operator therefore is operator assignment. Now what should it return? Mind you, assignment operator has the behavior that it can be chained. I can write this, right? And when you chain, what is the associativity of assignment operator? It is right associative. That is, C1 assigned C2 assigned C3 means C3 is assigned to C2, right associative. The result, which is the value that has been assigned, will be assigned to C1, right? So when I assign C1 to C2, the result that would return should be, I should be able to feed that result exactly back to the parameter of the same assignment operator. Right? So it must give me that object back. And that is the reason it has to be a reference, return by reference. It cannot be a return by call. If it were a return by call, then I will get a new object. But that is not what I want. I want my C2 object to change. Right? So that's a basic idea. So this is the purpose of the copy assignment. So now you look at the code. So first part of that is simple. Mind you, here, this is an operator function. This is not a constructor. So there is no initializer list because the object already exists. The object on which, the object C2 on which you have invoked this operator. So RE is assigned C dot RE. So when you do C2 assigned C1, what will happen is C2 dot RE is assigned C1 dot RE. Similarly for IM, this print message is just for our understanding so that we can see that a copy is happening. You can see this message below. And after that, what you'll have to return? After this assignment, it has to be the object C2 itself. You need that object itself. So you return that object. What is itself? Is start this. This is an address of the current object. So start this, dereferencing of that is the object. So that object has to be returned, and I cannot return it by value. If I return it by value, then what will happen? There will be a copy of that object made through the copy constructor, and I'll get a different object back. So that is not what I want. I want this particular object C2 to change. So I will return start this and return it by reference. So that is how a copy can be done, or assignments can be done, and they can now be chained on. So that's the basic idea. I'm going to the next slide, 24. So I try to do that in case of string. I have two strings, S1, S2. S1 points to football, S2 points to cricket. I can print them with their size, I can see. Now I want to assign S1 to S2. Now, when I assign S1 to S2, I know that I would need to do a deep copy, right? Because without a deep copy, that earlier kind of problems will happen, that if I just copy the str pointer of S1 into the str pointer of S2, then they both will start pointing to the same thing. And if I free up any one of them, the other one as a side effect will get corrupted. So I need to make a copy of that. Now the point is here S2 already exists. So it already has an allocation in S2 which points to cricket. Now if I just make a copy of football here from S1 and that new allocation I put here, the pointer which was pointing to cricket gets lost, but the system continues to know that cricket is allocated. This space is allocated. This 7 bytes are, or 8 bytes, 7 plus the null, 8 bytes are allocated. So what you'll have to do, you'll have to free up the str pointer on the assigned object S2 before you can actually do this allocation and copy. So you have to free str, so that will free up s2.str. Cricket is no more pointed to. Then you make a copy, duplicate copy, then you copy your length, and finally you return start this. So that will, so now if you do s2.print, it has become a copy of football, so it prints football. Right? If you do not do this free, then your resource will leak. Right? Because you will lose the pointer, but still the memory will remain allocated. Okay. Going to the next. Now the assignment operator allows you to do a self-assignment. I can do x assigned x. So I can do s1 assigned s1. Right? Suppose I have done that. I've done s1 assigned s1. That should be semantics wise. Syntax wise is perfectly okay. Semantics wise it should actually be perfectly fine. Right? But what happens when I do this? S1, I have S1 here, and I'm actually working on S1. So what I free is S1.str. And then I want to do a str dupe from S1.str. Because both objects are same. But it has already been freed up. The memory has already been released. So it's a garbage now. So this str dupe will now crash. So at this point, S1 assigned S1, you'll have a garbage printed. Because you have, or I mean, in the particular compiler I ran, it gave me a garbage. Your compiler, it could crash the program also at that exception point. So it is important when you are writing a copy assignment operator that you make sure that for self-assignment, you do nothing. So you need to check, I'm going to the next slide, 26, check that there is no self-assignment. And it is easy to do that because if S1 is assigned from S1, then the object on which you have called is S1, which has a pointer this. And object that you are passing to copy from is the object S, whose address is &s. So if it is a self copy, then this &s, the address of the formal parameter, and this pointer of the object on which you have invoked the copy assignment operator has to be same. So if they are same, you do nothing, just return start this because it's a self copy. If they are not, then they're different. So you do this function. So this is a typical way to write the copy assignment operator. And naturally, based on that, this is the typical signature of a copy assignment operator. It takes the argument by const reference, returns a non-const reference, and it returns start this. In between, it's thus this. You can it can also return, which is common. This is common, but it can also take a non-const parameter, in which case the copying might want to change the object it is copying from. There is again the move semantics come in there, and we'll talk about it in the context. These are different variants of the signature, which are occasionally in certain contexts may be used, but to your best of understanding, if you can remember this signature, that is the best thing you have done. So what we summarize with at the end, that now along with constructor and copy and destructor, we also have a copy constructor and a copy assignment operator, both of which, if not provided by the user, will be supplied free by the compiler, but with bit copy, shallow copy semantics, which may not be the right thing to do, particularly when you have pointer members and other embedded data member objects in your object layout. Right? So this is where I will have to stop. If there is a quick question, I can take. Otherwise, we will continue on the next class. Is there any question? I
Sir,
think just
while copying,
yeah,
there
yeah.
was c.re. We are using c.re, and re was a private member over there.
Yes, you are doing it in a data in a member function.
So the private is to class, not to the object.
Private is to the class, of course. Of course. Private is to the class. Because private tells you that you can, when you write the code for any member function, you can use them. But when you write the code for any other public function, global function, or any other function, member function of some other class, you will not be able to access it. That is the basic meaning. And object finally is an instantiation of values, right? So object is just data. It has no way to control anything. Object has nothing active. It is just a collection of it's just a bit pattern. It is the rules of compilation as imposed based on the declaration of the class is where you impose whether a private member can be accessed or cannot be accessed. Right? Okay, I think we have run out of time completely. We'll close here and meet tomorrow at 8 o'clock. See you then. Bye. Have a good day.